The topic is virtualization, virtual machine, hypervisor. What is virtualization? Virtualization is a technology that uses software, specifically a hypervisor, to create virtual simulated version of physical infrastructure such as servers, storage, and network on a single hardware system. By enabling multiple operating systems and applications to run simultaneously on one machine, it increases resource utilization, reduces hardware costs, boosts energy and efficiency, acts as the foundation for cloud computing. So simply, virtualization is the process, it's the technology that lets us trick our physical hardware, that is CPU, RAM, and the hard drive, into thinking it can be split up into multiple independent parts. Instead of having one big PC that only runs Windows, virtualization allows the same PC to run Windows, Linux, Mac OS all at the same time. So physical hardware has a lot of capacity resources that goes idle. To utilize those idle resources to its fullest, there is a concept of virtualization. Virtualization allows that idle resources or the resources in your hardware to utilize it to its fullest. We can create of virtual machines, so that virtual machines are another form of your computer or your interface that you can run or utilize that on another computer or another device. Virtual machines. A virtual machine VM is a software-based emulation of a physical computer that runs an operating system and applications completely isolated from the host machine. Using a hypervisor to allocate physical resources like CPU and RAM, virtual machines allows multiple operating systems, example Windows, Linux, Mac OS, etc., to coexist on a single computer. They are widely used for software testing, server consolidation, and secure computing. Simply, virtual machine is the result of virtualization. It is a software-defined computer that runs inside our physical one. It has its own operating system. It thinks it has its own dedicated hardware, but it doesn't have. It is inside a big hardware that is your physical hardware, and it just utilizes that resources from it. It is actually just a big file sitting on a real hard drive. If a virtual machine catches a virus or crashes, it doesn't hurt our physical computer. We can just delete the virtual machine and start over, which is why they are great for testing sketchy software or new updates. So that was about virtual machines. Now what is hypervisor? Hypervisor or virtual machine monitor VMM is a software, firmware or hardware that enables a single physical host machine to run multiple isolated virtual machines simultaneously. By abstracting and allocating physical resources, CPU, memory, and storage, it maximizes hardware utilization, reduces cost, and supports both enterprise data centers, that is type 1, and local desktop environments, that is type 2. Simply, hypervisor is a software that makes it all possible. It makes virtualization possible. It gives rights to virtual machines. If the physical hardware is a house, the hypervisor is the property manager. So what does the hypervisor do? It carves up the physical resource, giving, for example, 2 GB RAM to the virtual machine 1 and 4 GB RAM to the virtual machine 2. It makes sure that the virtual machines don't talk to each other unless they are supposed to. So they are independent to each other. Each virtual machine is not exactly dependent on each other for resources or anything. It depends on the physical server or physical hardware. It ensures that if one virtual machine crashes, the other keeps running smoothly. In other words, physical hardware in itself cannot perform tasks, or it cannot allocate, separate itself to create virtual machines. So we need something that communicates or creates virtual machines. So our hardware in itself cannot do a task unless we break it down physically. So it would not be of any use. To utilize physical hardware to its fullest, hypervisor is a software that communicates with the physical hardware or the physical server to let it create virtual machines and give rise to the concept of virtualization. Now let's summarize this. The concept physical computing, it has one family operating system, one whole plot of land, that is hardware. For virtualization, an apartment building, one plot of land is divided into many private units. The virtual machine, it is like the entire house. For virtualization, it is an individual apartment. It has its own door and kitchen but shares the building foundation. The foundation is hardware or the physical server. The hypervisor is the owner just lives there, the property manager. It decides who gets which room and makes sure everyone stays in their own space. Why does virtualization, virtual machines, or hypervisor matter to us? For efficiency, most servers only use about 10% of their power. Virtualization lets us use 90% by packing multiple virtual machines onto one server. For safety, we can run old, vulnerable software in a virtual machine without risking your main system or your main hardware that can get ruined by sketchy software on virtual machines and delete it if it doesn't work. Snapshots. We can save the state of a virtual machine. If we mess something up, we can hit undo or delete it and go back to exactly how it was 5 minutes ago. Virtual machines performance or its safety doesn't affect your physical hardware. Or the topic is drawbacks of virtual machines, isolation of operating system in virtual machines versus shared efficiency of operating system, containerization introduction, and the Docker lifecycle, and summary of. So what are the drawbacks of virtual machines? First, we must remember that virtual machines are really secure, a bit more secure and better than containerization in security because of isolation of software. However, virtual machines do have drawbacks. Drawbacks are related to resource management and resource utilization. Other than that, virtualization or virtual machines is also a great tool in comparison to containerization. For example, a server with 100 GB RAM and 100 CPUs using only virtual machines is like building 10 separate houses on a massive plot of each house needs its own plumbing, wiring, foundation. Even if no one is in the house, the utilities are still running. That is like wasting of money. In reality, a virtual machine might reserve 8 GB of RAM, but the app only uses 2 GB and that 6 GB is locked and can't be used by others. In comparison to containers gain, containers are elastic. If a container needs 2 GB, it takes 2 GB. If it doesn't need it, the resources stay available for the containers on that same host. So for example, if in an organization there are thousands of virtual machines that are running, each virtual machine isolates one application. Even if that application reaches its full potential, there might be some resources or memory CPUs that would be unutilized. If that was a scenario for one virtual machine, we would be okay with it. However, if an organization has multiple or thousands of virtual machines, then there is a lot of loss of resources as well as money. However, in containerization, one virtual machine can have multiple applications in it as a form of containers. So we manage to save a lot of resources. What is isolation versus shared efficiency? The operating system OS is the dividing line. Virtual machines provide hardware level isolation. Each has its own kernel. It is extremely secure but heavy because we are booting a whole operating system just to run one small app. As I said, virtual machines are really good for security. However, it is a complete isolation, so it would require complete booting of an app even if it is a small app. Each virtual machine has one operating system that has its own kernel. Kernel speaks with the hardware. You cannot speak directly with the hardware in itself. So you need kernel. So you speak to kernel and kernel speaks to the hardware to utilize resources and communicate. Whereas containers provide process level isolation. They share the host kernel. This makes them lightweight. They don't boot, they just restart. So for example, containers are inside a single virtual machine. For example, if a virtual machine has multiple applications that are divided into the containers, so each container wouldn't have a single operating system that would be really heavy, that would require boot. Each container would have a lightweight image that shares host's kernel, that is virtual machine's kernel. So it shares the resources from the host or virtual machine operating system. If it is Linux, it shares resources from it. Image of a Docker or container has libraries that are really lightweight in comparison to the virtual machines that require complete boot for a single app. In short, containers don't boot, they just start. Containerization and the Docker lifecycle. Containerization revolutionizes resource management by moving away from hardware virtualization, virtual machines, towards operating system level virtualization. Instead of over provisioning massive underutilized virtual machines, which leads to significant financial waste in large-scale environments. Organizations use containers to achieve high density. This allows them to run significantly more applications on the same physical hardware with minimal overhead. Containers are lightweight. Each container doesn't require another hardware or a single operating system to run it. It requires libraries, few resources from the host kernel or the host operating system, that is the single operating system of the virtual machine. So it is lightweight and efficient to use in comparison to the virtual machines. However, virtual machines are secure as it has isolation. Docker lifecycle. A Docker file. Docker file is a file containing instructions, for example, install Python, copy the code, etc. Docker image. When the Docker engine builds the Docker file, it creates a read-only portable snapshot that is called Docker image. Docker container. When we run the image or build it, it becomes a live container in the actual running instance of our app. In short, we create a Docker file with instructions of our application, and Docker engine builds that Docker file into a Docker image, and when we run it, it becomes a live container that is actually running instance of the application. So the summary, while containerization is more efficient, virtual machines still have a slight edge in security isolation. Since virtual machines have their own dedicated virtual hardware, it is much harder for a hacker to jump from one virtual machine to another. Whereas in containerization, because they share the same operating system, that is the same kernel, the walls between them are slightly thinner, though still very strong. The topic is architecture of Docker, Docker client, Docker host, Docker registry explained. This is the Docker architecture. We can observe that there exists Docker client, Docker host, Docker registry. In Docker client, there exist the commands we run, that is Docker run, Docker build, Docker pull. Docker host consists of Docker daemon, images, containers. Docker registry contains images, plugins. The Docker client. Docker client is the primary interface through which users interact with the Docker system. It is part of Docker's client server architecture and provides the means to issue commands and manage Docker objects like images, containers, and networks. In short, it is the primary way we interact with Docker. When we type a command like Docker run or Docker build into our terminal, we are using the client. Its job, it acts as the interface. It doesn't actually run containers itself. It just sends your request to the Docker host. Flexibility, that a client can sit on our laptop while communicating with the Docker host running on a completely different server or in the cloud. To understand Docker client, we must know that Docker or Docker daemon is the main heart of the Docker that functions, and its job is to do the heavy lifting, manage the core Docker functionality. So Docker client helps translating user commands from the CLI or the terminal, or it translates user commands into REST API request, and it sends that to the Docker daemon. In short, Docker daemon does all the heavy lifting. It is the heart. It manages the core Docker functionality. However, Docker D cannot translate user request or user commands. It needs Docker client to translate those commands or user commands from the CLI or the terminal that gets the REST API request, which is understood by the Docker daemon. The Docker host. A Docker host is a physical or virtual machine on which Docker engine is installed and running. It is the foundational infrastructure that provides the necessary resources, CPU, memory, storage, and networking for Docker to run and manage containers. In short, it is the machine, physical or virtual, that provides the environment to execute our applications. This is where the magic happens. Docker host provides the environment for core components of the Docker platform to operate. Those core components are Docker daemon or Docker D, operating system kernel, physical resources like RAM, CPU, storage, etc. Docker host uses specific Linux kernel features to provide the necessary isolation and resource management for containers. Docker engine uses namespaces to provide an isolated workspace for each container. That ensures each container has its own view of operating system, including separate process IDs, network interfaces, and mount points. For resource management in containers, it uses C groups, that is control groups, that is used to limit and manage the amount of host resources like CPU and memory that a container can consume. This ensures that fair resource sharing and preventing a single container from overwhelming the system. In short, for resource management, Docker host or containerization or Docker solves the issue that was within the virtual machine or virtualization, where we could be running multiple applications in a single virtual machine. However, there was not a good amount of isolation inside a virtual machine which the containerization or Docker host provides. So this is the features offered by containerization, whereas in virtual machines, if you run multiple applications, each resources would be enmeshed so much that the system may lag or even shut down. However, in containerization, Docker host does the isolation, does the resource management, so that the system doesn't get overwhelmed. How it does? It ensures fair resource sharing. It limits and manages an amount of host resources, CPU and memory that a container can consume, which eventually prevents a single container from overwhelming or affecting the system performance. Docker host so does the networking. That is, the Docker host is responsible for managing container networking. It sets up a virtual bridge network to allow communication between the containers and external networks via host connection. It handles port mapping, which allows services within a container to be accessed from outside the host machine using a specific port on the host IP address. Docker host has the operating system kernel, which means containers running on the Docker host share the hosts, that is virtual machines operating system kernel. That makes the containers lightweight compared to the traditional virtual machines, which requires a full separate guest operating system for each instance. For physical resources, Docker host uses the host machine, that is virtual machines, CPU, RAM, and storage for managing various containers running on it. Docker daemon or Docker D. Docker D listens to the Docker API requests from the client and manages objects like images, container networks, and volumes. Docker D is the background service that runs on hosts, machine, and manages all Docker objects such as images, containers, networks, volumes. The Docker client communicates with the daemon to execute the commands. That is, Docker client translates API requests from the CLI or the terminal from the user, so the Docker daemon performs the action. Docker registries. A Docker registry is a centralized storage and distribution system for Docker images. It acts like a digital library for an app store for container images, allowing developers to store and manage and share their containerized applications across different environments. In short, it is a storage and distribution system for our Docker images. If we need a specific environment like Python or Nginx, we usually pull it from a registry. Public registries. Docker Hub is the biggest one. It is a default registry where anyone can find and share images. Private registries. Most companies use private registries like Amazon ECR or Google Container Registry to keep their proprietary code and internal tools secure. Simply, Docker Hub contains images same as GitHub that contains source code. The difference is Docker Hub is used for images and containerization, whereas GitHub is used for application, software development, web development, and source code. Docker Hub contains number of public registries or public images that can be used. We must know that a Docker file contains the instructions and image is the blueprint or the recipe of that instructions in a Docker file. When we run that Docker image, it forms the Docker container, which is like the running instance or the live execution of that image. Docker images are composed of series of read-only layers where each layer represents instructions that are inside a Docker file. Docker images are highly portable and can run consistently on any system, developers, laptops, test servers, etc. that has Docker engine installed, regardless of the underlying infrastructure. Users can store Docker images in the Docker Hub. Docker Hub is the default public registry that offers vast number of libraries of official and community contributed images. We can modify the visibility of Docker image in the Docker registries or in the Docker Hub. We can either make it public for every users to download and utilize and use that Docker image to run a container. However, we can also make that registry or a Docker image in the Docker Hub private, so only you can view and use it. The concept of Docker private registry is to restrict access to only authorized users and systems. A private registry can either be hosted internally on-premise or through a cloud service, AWS, Google, that offers controlled and restricted access to images. Organizations use these private registries for enhanced security, performance, and control over their software supply chain. This ensures that only authorized team members or systems can push or pull images, protecting sensitive or proprietary software components. How they work together. Pull. We tell the client to get an image. Fetch. The host reaches out to the registry and downloads the image. Run. The host turns that image into a running container. So we tell the Docker client to get an image to the terminal or the CLI. That Docker client translates that commands into the API that is understood by the Docker daemon that reaches out to the registry and downloads that image. Later, the host turns that image into a running container. The topic is multi-stage Docker build and Docker Compose. Explain why we need multi-stage Docker build and why multi-stage so important. And I will explain the concept of Docker Compose. Multi-stage Docker build. Multi-stage builds are a powerful Docker feature that allows us to use multiple from statements in a single Docker file to create optimized, minimal, and secure production images. This technique separates the build environment, which often requires large compilers and SDKs, from the final lean runtime environment. How this works? This has multiple stages. A single Dockerfile includes multiple from instructions, each beginning a new build stage. Naming stages. Stages can be named using as or as space name of it. For example, it would be from Golang 1.22 Alpine as builder for easier reference. So the Golang 1.22 Alpine would be referenced or will be given a short form, that is builder, as a reference. Selective copying. The key is the copy from stage name or the number instruction. This command copies only the necessary artifacts, like that is compiled binary or production ready files, from an earlier stage into the later, typically much smaller stage. Final image. The resulting image is solely based on the last stage defined in the Dockerfile, discarding all the intermediate stages and their unnecessary build tools and dependencies. It was about multi-stage Docker build, its definition, how this works. Now I'll explain in a simple example how this works. We must know that the purpose of a Dockerfile is to containerize the application. So when that image is built and run, so it creates a container, and that container is the app in itself. If we create a Dockerfile, only one stage that has build and runtime, that would be a really heavy process, or that take up a lot of space in an application to run. We need build features or binaries that are really important. I get it, but we only need that for a runtime environment, not throughout the process. So multi-stage Docker build separates that each stage. So the first stage gives us the artifacts or the gold, and the second stage, that is the runtime, that extracts that gold. So it only takes that information as a gold to create a runtime environment. So that runtime environment is stage that is taken as the final stage, so the image is lightweight. Another example, imagine you want to have exotic food and you don't know how to cook. So you hired a cook to give you that food. So he said like, yeah, I can cook and give you that food and prepare that food for you. So he said like, I would charge 500 rupees for cooking that food. So you said like, yeah, that's reasonable. However, you thought like, I don't want to go and buy the groceries, the spices, the vegetables, and each ingredient in it. So you don't have anything in your kitchen. So you said like, yeah, you are cooking for 5,000, but I also want you to go and bring each ingredient from the grocery store and also try to negotiate the prices, etc. All this headache should be managed by you. So you first bring those ingredients which I don't have in my kitchen. Then you start to prepare the food, and you expect like he would say, yeah, I would do that for free. I would only charge for the cooking. But it is not the case. He said, no, I would not be doing it. I said I would only cook the food. So if you want me to bring all those ingredients from the grocery store and negotiate to its prices as well, and then cook the food, I would charge 50,000 from bringing those ingredients and only 5,000 for cooking it. So you are like, cooking it's less costly than bringing those ingredients, but you only want to have food. Analyze the example. I just exaggerated the cost so you can have the understanding of it. So this is the case with multi-stage Docker builds. So if it was a single process
it would be like the chef would bring all those ingredients, then start to cook the food, and he would charge you 55,000 rupees. And you say like, yeah, I'm okay with it, I will pay for it. So in our Dockerfile example, you would be utilizing a lot of storage, which is similar to 55,000 rupees. So if the situation was different and it is multi-stage Docker build, so the situation that would happen would be the chef would do the usual step of negotiating and bringing each ingredient into your kitchen and then start to cook the food. That's the same. However, when the chef enters the kitchen, magically he forgets that he has to charge you extra 50,000 for bringing those ingredients. He just charges you for cooking the food. So the magic that is happening is the separation of two steps in a multi-stage Docker build. So in that separation, we only take the result, that is the ingredients which we get from the stage 1, and we utilize those ingredients and cook the food, which would be like the runtime environment of the second stage, and we build the image from that final stage. So here's the example, that is Go application. This is a common use case with compilation language like Go or Java, where the compiler is not needed at runtime. So the first stage is building the application with the full SDKs and binaries. From Golang 1.22 Alpine, this is the lightweight Alpine Linux with Go SDK. So we're extracting that Alpine image and we are giving it a reference as builder. So second line is work dir, that is the working directory, that is /app. We want to have a separate directory, that is /app. Third is copy go.mod space go.sum space ./ That means copying the dependency files first so Docker can cache the dependencies. Copy ... that copies the rest of the source code. Then that is run command. cgo enabled equals to 0. That means disabled C bindings, making the binary full static. GOOS is equals to Linux. This ensures that the binary is built for Linux. Go build space -o /app/server space ./cmd/server. That means that compiles the Go application into a single binary called server. So this stage is a heavy stage where you are using the dependencies, SDKs, same as getting all those ingredients and compiling it into a server. Stage 2, creating a minimal runtime image from scratch. Scratch, that is an empty image, no operating system, no libraries. Working directory space /app. So /app is the working directory. Copy from equals builder space /app/server dot. This is the most important step. That's where the magic happens. So it says it only copies the compiled binary from the stage 1. Simply, we are only taking the ingredients we got from the negotiations, from going to the shopping, going to the grocery store. We are only taking the ingredients we got from the stage 1, and we are discarding all those heavy work or the hard work we have done to get those ingredients. So we are only taking those results from the stage 1, that in short is called the compiled binary from the stage 1. So we are only copying those, and then expose 8080. Application will run on port 8080. Entry point /app/server. This defines the binary as the container's main process. So if we only had one from statement, everything that is Go SDK, build tools, source code, dependencies, compiled library or compiled binary would live together in the final stage. That means the container would be big and heavy because it carries all the build time baggage, even though we only need the final binary at the runtime. With multi-stage builds, We isolate the heavy build environment from the stage 1, from the runtime environment that is light, stage 2. So stage 1 would be using a full Go SDK image to compile a binary. Stage 2 would be starting fresh, here that is scratch, and copy only the compiled binary from the stage 1. The result would be the final image that is lightweight, that is just your binary plus maybe a few metadata layers. All the heaviness of the compilers, libraries and caches is discarded because Docker only keeps the last stage as the runtime image. So you can fit in the example which I gave about the chef and ingredients, which exactly matches this entire process as a reference. Make sure to like, share and subscribe because of this simple explanation. Sorry for the plugin, whatever. So yeah, next is the benefits of multi-stage builds. Smaller image sizes significantly reduces the final image size by leaving behind build time dependencies, leading to faster transfer and deployment times. Enhance security. A smaller image has reduced attack surface because it only contains fewer packages and tools that could have vulnerabilities. Simplified Dockerfiles. It consolidates the entire build process into a single Docker file, eliminating the need for separate build scripts or multiple Docker files, for example, one for development and one for production. Improved caching. Docker can cache immediate layers more efficiently, speeding up the subsequent builds, especially when the source code changes frequently but dependencies do not. So that was about multi-stage Docker build. Now let's understand what is Docker Compose. Docker Compose is a tool for defining and running multiple container Docker applications using a single YAML configuration file, typically named compose.yaml. This simplifies the management of application stacks like a web service and a database that requires multiple containers to run and communicate with each other. So let's take the same example of our chef and our exotic dish. We needed the exotic dish as a result, or we want that dish for us to eat. But to specify that dish includes a mojito, a dessert, a salad, and the main course. That is, in short, the food that you want. So the chef said, I will bring those to you after cooking. But the catch is, he said that he will only bring each one after the other, bringing you one juice first in your table. Then after that, he would go and then bring the salad. He will go and then he will bring the main course of the meal. He will go again and bring the dessert. So in that example, it's only limited to taking time to go and bring those food that you ordered. But in reality, that would mean you have multiple containers that are running. That is a separate container for web services, that is like a front end, and also for the backend database. So you have at least two containers that are running. Instead of running each container one by one and then utilizing your application, or in our example, getting each ingredient one by one and then having a meal, or using Docker Compose, that is like saying the chef to bring all those food in a single tray. So it would be like he would be bringing salad, main course, the juice and a dessert at one time. So it's similar to that. In Docker Compose, we create a YAML file, that is compose.yaml, that simplifies the container process into running a single compose file, which means you don't need to run each container. You only need to create a YAML file, specify the information in it, and then run the compose.yaml. So after running those compose.yaml,
your both containers would communicate with each other and run at the same time, and your application would be running. In short, to run multiple containers that communicates with each other, so instead of running each container one by one and providing the result, so we skip all those hard work and we create a compose.yaml, that is docker compose.yaml, and we specify some steps in it. After we run that one compose.yaml, that would result in running all the containers, at least the two I specified, that is like the web service and a database, at the same time that communicates with each other, that serves the application. Key concepts in Docker Compose. Declarative configuration. Instead of using multiple complex Docker run commands, you define all your services, networks, and volumes in one file. This file acts as a blueprint, ensuring consistency across different environments, development, testing, production. Service definition. The service section in the compose file defines each container that makes up our application. We can specify image to use or a Docker file to build from. Exposed ports, volumes, and environment variables. Single command execution. A single command, docker compose up build, which builds and starts. Docker compose creates and starts all the defined services and their dependencies. Networking. By default, compose creates a single network for your application, allowing containers to communicate with each other using their service names. So Docker compose simplifies the process, so we don't need to use complex Docker run commands. Instead, we define all our services, networks, and volumes in one file. So that file, Docker compose file, acts as a blueprint that ensures consistency across different environments. That compose file has service definition. In that service section, the compose file, we specify the image to use. The ports, volumes, and environment variables all are defined in the service section. And it's a single command execution. For networking, Docker Compose creates a single network that allows containers to communicate with each other using the service names. In my next video, I will be showing you Docker Compose as well as the Dockerfile or multistage of my own application that I built, so you can have better understanding of this concept. Common commands for Docker Compose. Docker Compose provides commands for managing the full lifecycle of our application stack. Docker Compose up builds, if necessary, creates, starts, and attaches to the container for a service. Uses the D flag to run in the background or in the detached mode. Docker Compose down. This stops and removes containers, networks, and if specified with volumes, the volumes created by it. So it stops. Docker Compose PS. This lists all the containers in the current project, showing the state and port mappings. Docker Compose logs. This allows us to view the logs as an output from containers. Docker Compose up build. This builds the images for our services. In short, Docker Compose allows or multiple containers that are created instead of running each container one by one, and or at least starting each container one by one and then run our application. We specify certain information in the service section that includes environment variables, ports in it to run all containers at the same time that communicates with each other. The topic is containerizing multi-stage Docker build and Docker Compose for full stack React, Express, JavaScript application, that is Resume Matcher. This full stack application was built by me a few months ago. Now let's containerize it. I will explain you the Dockerfile, the Docker Compose, and the Docker ignore of this containerized application, and we will run this container to see how it works. So let's understand the Dockerfile. We must know that the purpose of Dockerfile is to create a blueprint of our application. The Dockerfile consists of syntax and it creates application in a container.
You create a Docker file, you build it, and it becomes an image. When you run that image, it becomes a container, which is an app in itself. So your application would become a container, and that container would be a functioning app of yours. Dockerfile is something where you give steps and you give dependencies, builds, runtime environment, all these steps in a Docker file, which helps it in building your application in a container. So Dockerfile acts as a blueprint for your containerized application. So now for my application, that is Resume Manager, let's understand its multi-stage Docker build steps. My application is a multi-stage build. The purpose for multi-stage was to balance the small image size with the compatibility for the native modules, which were like Sharp. That depends on library VIPS and glibc. So that was about the Dockerfile. Now let's understand what is the purpose of multi-stage builds. The importance of multi-stage is to break down Dockerfile into stages, and final stage is the runtime environment. So we take the artifacts from the build stage and we utilize those artifacts to the last stage or the final stage, where we create a runtime environment from those build artifacts. So the image is lean and lightweight. Stage 1 is the build stage, where we build from Node 20 Alpine as builder. As builder is the reference. Builder is the reference for our Node 20 Alpine base image. Workdir is the working directory, that is /app. This uses Node 20.js 20 Alpine, which is a lightweight base image, and it sets /app as the working directory. So there exist multiple technical stacks, which includes Python, Flask, Node.js or React.js, etc. So mine is a Node.js application, so it is a JavaScript. So my Dockerfile build or multi-stage build will be based on those JS commands or those syntaxes. Now run apk add no cache / that is the current folder, followed by Python 3 until fftw -dev, followed by build base. So this command is used to install build tools and libraries that are needed to compile native modules, that is Sharp, for my application. So Python 3 make G++ R compilation tools. VIPS -dev fftw is a dependencies for libvips that is used by Sharp of my application. Build base. This is the meta package with essential compilers and libraries. Basically, run apk add is to install build tools and libraries and native modules for my application. Copy package star.json followed by / run npm ci. This command is for copying the dependencies manifest. Run package.json contains the dependency manifest, so it copies it into the current folder. npm ci is for clean reproducible install, which is better than npm install. Copy ... followed by run npm run build. This is to copy the entire steps which we did from the from statement until these steps. So it copies all of this into the current, and that run command builds the project. So that was about the build stage. So this build stage gives us essential libraries and build tools which would help us in the later stage, that is the later stage of or the final stage, to create a runtime environment
from those build stage artifacts. Stage 2, which is runtime, from Node 20 Slim workdir, that is /app. This switches to Node.js 20 Slim, which is a Debian based. Debian Slim is chosen because it uses glibc, which ensures that sharp works correctly at runtime. It is based on the dependencies and working of my application, so Debian Slim works better in my runtime, so it is used. And working directory is /app, and multiple copy statements until package.json. This copies only the build output and necessary files from the build stage. So only necessary artifacts or build output from the build stage is copied. This keeps the runtime image lean, no redundant dependencies that would increase the image size and make it heavy. So it only uses necessary files from the build stage to create a runtime environment. Run npm CI only production. This installs only production dependencies, which ensures sharp is rebuilt correctly against glibc, which is simply installing only the production dependencies for lean image or lightweight image. Expose 3000 cmd node server.js. This exposes port 3000 for the application, which runs server as an entry point. It simply means that the application would run on port 3000. Alpine for building, that is lightweight, fast builds. Debian Slim for the runtime. This is for the compatibility for the sharp dependency. Multistage build. The purpose of multistage was to keep the final image small by excluding build tools and developer dependencies. npm CI. This is for reproducible installs. This avoids dependency drift. In short, this Dockerfile compiles of sharp in Alpine with all build tools, then runs the application in Debian Slim for glibc compatibility, which ensures a small production-ready image that works reliably with native modules. Now let's understand Dockerignore or Dockerignore. Dockerignore file tells the Docker which file and directories to exclude from the build context when sending data to the Docker daemon. Dockerignore helps to keep the images smaller, builds faster, and avoids leaking sensitive files. So we have ignored node_modules. This excludes node modules because dependencies are installed inside the container, that is npm CI, not copied from my local machine. This prevents from bloating the image with host specific modules. Node modules are ignored because it includes host specific modules, which is required to run in a local machine or my system. We are containerizing the application, so we don't need those dependencies that are required for running in the local machine. Prevents from bloating the image or increasing the image size. TMP, in short, distribution and temporary. This excludes compiled or build files from the distribution and temporary files. This excludes compiled or build files, that is distribution and temporary files. Ensures only source code is copied and container builds fresh output. .env excludes env file, environment variable files, which contains secrets of database passwords and API keys. This is to prevent accidental leakage into the image layers. So the environment variable has sensitive data of the API keys and database password. To prevent it from accidentally leaking into the image layers, we have ignored it in the Dockerignore. Logs, that is .log npm yarn debug yarn error. This excludes log files generated during the development. This keeps the image clean and avoids unnecessary clutter. .git ignore .git. This excludes Git repository metadata and ignores rules. These repository metadata and ignore rules are not needed inside the container. Operating system files, that is .ts store thumbs.db. This excludes operating system specific chunk files, Mac OS, that is .ds store, Windows thumbs.db, IDE or editor configurations, that is .vscode.idea. This excludes editor setting or configurations, VS Code, prints. This keeps the container environment independent of developers' IDE. Test, docs, coverage. This excludes test files, documentation, and coverage report. These are not needed in the production builds. Finally, deployment specific, that is .virtual. This excludes development. This excludes deployment metadata, which is like the virtual configuration. This keeps the container focused on the runtime code only. Docker ignore step is important because it helps in keeping the smaller build context, cleaner images, and better security. Now Docker Compose. We know that Dockerfile creates an image and runs a container. When there are multiple containers and all of those containers depends on each other, instead of manually starting each container by complex Docker commands, we create a Docker Compose file. That Docker Compose file contains commands which is composed of a single command. It turns on or starts all those containers which communicates with itself, so we don't have to start each container one by one. So our Docker Compose file consists of 3 service stack, that is 3 containers, Node.js application, which is web, a Postgres database, DB, and Nginx reverse proxy, naming Nginx. I have explained the concept of multistage Docker build and Docker Compose in my previous video. You can watch those videos so you can have understanding of concept, Docker Compose, and multistage build. Which means our containerized application will be running on 3 containers. First, that is web, second, DB, and third, Nginx. So these services will be defined in the Docker Compose file. So first is web build space dot. This builds from the local Dockerfile. Maps port 3000 on the host to the containers port 3000. env file loads environment variables from .env, which includes API keys and database passwords. Networks AppNet, which means connected to AppNet network for internal communication. Health checks. This calls /health endpoint every 30 seconds. If it fails 3 times, container is marked unhealthy. That was about web as a service in a Docker Compose file. Now DB service stack in a Docker Compose file. It uses Postgres 15 Alpine, that is lightweight, as an base image. env file loads the credentials or configurations from .env. Volumes persistent data in a named volume DB data. We need something to store our data. So DB data is the named volume where the database data would be stored, and the actual path is /var/lib/postgresql/data. It stores the persistent data. Networks, that is AppNet, which means it is connected to the AppNet network. Health checks. This runs pg underscore is ready, which means Postgres is ready to verify database is accepting connections or not. Also has AppNet as a network. So this AppNet would help in communication between these 3 containers. Now Nginx as a service stack in a Compose file. This uses Nginx Alpine as a base image and maps port 80 on host and containers port 80. This mounts a custom Nginx configuration, that is default.config, into containers read-only. Depends on web. This ensures that app is up before proxy starts. That means Nginx as a service depends on web as a service stack, which I explained before. So when the web as a service container is up and running and it passes health checks, then this Nginx proxy service starts. So it depends on that web. Connected, that is AppNet. Networks, that is AppNet, which means it is connected to AppNet as a network. Health checks, this pings / every 30 seconds, which means it pings the root, that is localhost, every 30 seconds. Volumes and networks. Volumes, that is DB data. Networks, that is AppNet. DB data, this is the named volume for persistent Postgres storage. AppNet, This is a custom bridge network, so containers can talk to each other by service name, web, DB, Nginx. So AppNet is a network bridge that helps containers talk to each other by their service name, which is like the web, DB, and the Nginx. In short, web runs Node.js app, DB handles persistence, that is DB data. Nginx serves as a reverse proxy or the load balancer. Health checks ensure services are actually ready before others depend on them. Named volume keeps DB data safe across container restarts. Custom network isolates application stack from other containers. This compose setup gives us a production style mini stack that is like a Node.js application behind Nginx backed by Postgres, all wired together with health checks and persistent storage. So that was about the explanation of this Dockerfile, Dockerignore and Docker Compose. Now let's run this application to see if it is even working or not. First, you must know that after you create a Docker Compose file with Dockerfile and Dockerignore, the first command you should run is docker compose up build. So that would build and then run. So I've already built and run my container before. So I'll just do docker compose up to see how it works. I switched into my directory. Now you can see like DB, Nginx, web. That are the three service stack or the containers that are running and that are interconnected or that communicates with each other with AppNet network bridge. Now let's confirm it by going into the localhost 3000 as it is serving and running on port 3000. As you can see, it is healthy and running on port 3000. Let's confirm it by adding a resume into it. As you can see, results are also visible, which means the application is up and running perfectly fine. As you can see, this is the results of my resume. Now let's check and see the logs. As you can see in the logs as well, it is up and running perfectly fine. When I do Control C, it stops this. Now it's stopped. Let's check again. Now it's not running. We can see in our Docker desktop application, our container is stopped. The topic is understanding Dockerfile of well-known tech stacks, that is Node.js, Python, Go language, Java, Spring Boot, Rust, WASM or WebAssembly, and AI or ML. Also, we will understand what is interpreted versus compiled language. We will compare Node.js, JavaScript, Dockerfile with all these other well-known languages and tech stacks so we can have understanding of the Dockerfile concept. First is Node.js or JavaScript. I have already made a video on Node.js, JavaScript, Dockerfile concept and containerized application of the JavaScript or the Node.js of my major application. I have made a detailed video. You can watch that video so you can have idea on this JavaScript in detail. I have also made a video on multi-stage builds. What is multi-stage build and how it is different from a single Dockerfile with a single stage or in the single build. You can watch these both videos first to have idea on these basics of Dockerfile multi-stage build and at least Node.js or JavaScript Dockerfile, because I will be explaining the concepts with respect to that Node.js comparison. However, I will give you a basic understanding of this, that is JavaScript. So first is stage 1, that is builder stage, and we have stage 2, that is runtime. Why do we have two stages in this Dockerfile? Because we have implemented the concept of multi-stage build. Multi-stage build says that create stages in a Dockerfile so the image is lean, lightweight and more secure. If we had implemented a single stage Dockerfile, it would be really heavy because it would have unnecessary build tools, build binaries that are actually not required in the runtime. runtime environment. So multi-stage build differentiates these in the stages. So in the final stage, we only take the artifacts or the build tools that are required. So the image is small. In the first stage, we install build dependencies, libraries, etc. We copy the packages, we create the build, all these steps in the first stage, and there comes the second stage or the final stage where we only use the required files from the stage 1. That means we only copy the build output and package manifest from the stage 1. So instead of copying everything from the stage 1, that would bloat or make the image heavy. We only copy the required build output from the stage 1, so the image is small. That was basic understanding of multi-stage build. Now let's understand this. This Node.js Dockerfile also has 2 stages. First stage is builder stage and second is the runtime stage. In the first stage, we have use from statement, that is the base image, and referenced it as the builder. Working directory is /app run apk until build base. This is to install the dependencies required for my application. Copy package run npm ci. This is to copy the manifest and install the dependencies for my application. Copy dot is to copy entire steps, entire what we did into the current folder. Run npm build, npm run build is to run and build this stage 1. That was about stage 1. Now stage 2, the runtime. Same, we have taken node 20 slim, that is the base image. Working directory is /app. Here comes the main part, that is we only copy the build output from the stage 1 in the second stage, so the image is small. We have copied distribution until package.json. So these are the build output that are required. Run npm ci only production. This only installs the production dependencies required. Expose 3000. This is to expose port 3000. That means application will run on port 3000. cmd code server.js. cmd means command. Whatever inside the cmd simply is command used to run our application locally. While building this application, resume matcher to debug or to fix the application. While building the application, I ran my application by using node server.js in my command prompt while I was in the application folder. And while running node server.js, it activated backend as well as the front end. So here cmd also does the same. It activates that node server.js command. So the application is running. I have that idea because I have ran my application locally in the cmd. After doing this node server.js, my application was running on the port localhost. In the here cmd does the same thing. It runs this command and the application runs on the port 3000. So that was about JS or Node.js. Now let's understand Python Dockerfile and compare it with the Node.js Dockerfile. Python doesn't build a binary. Here we build a virtual environment to keep the final image clean of compilers. Here is a Dockerfile of a Python application. It also has multi-stage build, that is stage 1 builder, stage 2 runtime, stage 1 builder. Here base image is Python 3.11 slim, which is lightweight Python image. Installing build tools. Build essential provides compilers and libraries needed to build Python packages with native extensions, that is NumPy, Pandas, SciPy. So build essentials provide the compilers and libraries that are needed to build Python packages with native extensions. Virtual environment. This creates V environment at opt/vnv, so dependencies are isolated. Path update. This ensures that VNV's binaries are used instead of systems. Python copy requirements. This brings requirements.txt. Install dependencies. This installs all Python packages into the VNV without caching to reduce image size. So this stage is only for building dependencies. It won't be the part of the final runtime image. So it's same like it has a builder stage and it has a runtime environment stage. Stage 2, that is base image. Again, this starts from Python. This starts fresh from Python 3.11 slim. There are no build tools here. Copy the VNV. This brings the pre-built virtual environment from the builder stage. This is same as the previous Node.js one. Here we copy the pre-built virtual environment from the previous stage or the builder stage. Means we only take the required artifacts from the previous stage, so the image is lean, and lightweight. Path update. This ensures runtime uses VNV packages. Copy application code. This copies projects files into the /app set working directory. /app becomes the default directory. Default command. This runs Python app.py when the container starts. So this stage is clean and lightweight. It only contains Python, the application, and the dependencies. No compilers or build tools remain, so the image is lightweight. Let's compare it with the Node.js Dockerfile approach. What's same between them? Multi-stage build. Both are split into the builder and runtime stages to keep the final image slim. Base image choice. This starts with language runtime. For example, in Node.js approach, we have used Node 18, and in Python we have used 3.11 slim. Dependency installation in builder, which is in Node we have used npm install for dependency installation in the builder stage, whereas in Python we have used pip install inside a virtual environment. That means npm install is for Node and pip install is for Python. Copying build artifacts. In Node we copy the whole /app directory. In Python we copy the virtual environment, that is /opt/venv, and the app code. Runtime stage is minimal. No compilers, only the language runtime plus dependencies plus app code. CMD defines the default process. For example, in Node, as I mentioned, node server.js would mean that when we run our application locally, we use this command node server.js. So the application would run on port 3000. It's same in the Python. Instead of server.js, node server.js, we use python app.py to do the same what CMD does in Node server.js. What's different between these Node.js and Python Dockerfile? The concept of dependency manager. In Node.js we use npm or yarn. In Python we use pip dependency file. In Node.js we have package.json or package lock.json, whereas in Python we have requirements.txt. Build tools. In Node.js usually not needed unless native modules. Python explicitly installs build essentials for compiling C extensions. Isolation. Node modules live in the node underscore modules, whereas in Python dependencies installed into a VNV, that is /opt/venv. Runtime copy. This copies application plus node modules. In Python, this copies application plus virtual environment. Execution command, that is node server.js node and python app.py in Python. Summary of Python Dockerfile. So Python Dockerfile is doing the same job as Node, but in stage 1, that is npm install in Node. In Python, it is pip install into a virtual environment. In stage 2, slim runtime, that is Node 18 slim. Python uses 3.11 slim. Instead of node modules, Python has VNV directory that gets copied over. So both Node.js and Python are similar also because they are both interpreter language type, whereas the languages we discuss later are compiled. That would be a slightly different concept. Now let's understand what is interpreted versus compiled languages. In interpreted languages like Node.js or Python, for our application to be understood in your runtime environment, for our application to be run, it needs to be understood by the system. So in Python and Node.js applications, for the system to understand your application so it runs it, it must understand the language of your application. For example, if you want to run the application that is Node.js, your system or your runtime environment also must understand Node.js as a language. If it is Python, it would be the same. Your runtime environment must understand Python, whereas in compilation or compiled languages, it is not like that. In compilation, your application is compiled into a single binary, so the application is only understood in the primitive level that is the binary language, that is zeros and ones. Instead of needing a specific language, Node, Python, C, etc. languages, it only understands application on zeros and ones, that is binary language or machine code or bytecode, which means the application image size in the compilation languages is smaller compared to interpreted languages. Let's understand it deeper. Execution model in Node.js, Python or interpreted languages. Source code is read and executed directly by a runtime Node.js engine or Python interpreter. Whereas in compilation languages, that is Go, Rust, Java, WASM, source code is transformed into a binary machine code or bytecode before execution. Runtime dependency. Interpreted languages needs the language runtime inside the container, that is Node Python, whereas in compiled languages, because binary is self-contained, runtime may be optional. For Go or Rust, runtime dependencies are not needed, is required only for Java, that is Java Virtual Machine. Dockerfile builder stage. In interpreted Node.js or Python, mostly installs dependencies, npm install, pip install, no heavy compilation step. Whereas in compiled languages, it compiles into an artifact, that is Go build, cargo build, mvn package. Interpreted languages doesn't have heavy compilation step, because we already have an interpreter or engine that understands your application's language, so it doesn't need much of a compilation, as the application is run by the interpreter or is understood by the interpreter. Whereas compiled languages, the application must be compiled first and then the application would be converted into the binary language, and that must be understood by the binary language in the zeros and ones. So it first needs compilation, then to be understood it is converted into the zeros and ones in the binary language. So it requires compilation first in the compiled, whereas it is not required in the interpreter. Dockerfile runtime stage. Interpreter must include the runtime image Node 18 Slim or Python 18, Python 3.11 Slim. Whereas in compiled languages, it is often just scratch or minimal base, that is Debian Slim with the binary. In interpreter languages, we must be using or we must include runtime image, or we must specify the runtime image. In Node.js, we must specify the Node 18 Slim, or in Python 3.11 Slim, or whatever image we are using. Whereas in compiled languages, we don't need that. In compiled languages, the runtime image can be scratch, that is just empty. Scratch means nothing, it is empty. Or it can be minimal base Debian Slim, which makes the compiled languages or image size of the compiled languages a lot smaller and lightweight compared to the interpreted languages. Docker image. Output artifact. App code plus dependency folder, that is node underscore modules, Python env. In compiled, that is single binary or package artifact, that is name app.jar, app.wasm. This is what I've explained before. Interpreted languages has certain folders, that is node modules for node that has dependencies, Python env that has Python environments. We have those in the Python and node because it is an interpreter languages, and that interpreter can understand the node folders without compilation, as it understands the language of your code, because the runtime must be your application languages. Whereas in compiled languages, the application or the code is first compiled a single binary or a single packaged artifact, that is main or app.jar or app.wasm, because when that app in that compiled languages is in a single packaged format, then only it can be compiled into the binary or machine code. So the application is compiled into a single artifact, then that single artifact is transformed into a binary machine code or bytecode before its execution. Image size. Image size in interpreter languages is larger because of the runtime plus dependencies that are must, whereas in compiled languages, image size is smaller because only binary is shipped. Portability. Interpreter languages needs runtime installed wherever it runs, whereas in compiled languages, binary can run anywhere with compatible operating system or CPU or WSI host for WSM. As mentioned, Node.js, Python are interpreter languages that needs a runtime that understand its language, whereas in compiled applications that run on compiled understands only the binary or machine code or byte code, so it can be run anywhere with a compatible operating system or the CPU that supports or WSI host for WSM. So why this matters in Docker files? Node or Python, Docker files always copy both code and dependencies, then rely on the runtime image to execute. Go, Rust, WSM. Docker files focus on producing a binary in the builder stage, then ship only that binary into a minimum runtime image. In Java, compile to, but instead of native binary, it produces bytecode jar that still requires the JVM runtime, EIML or Python. Even though Python is interpreted, the runtime image is heavy because it must include CUDA libraries and machine learning frameworks. That was about compilation versus interpreted languages. Now Golang. Let's understand Go language Dockerfile and compare it with the Node.js Dockerfile. We move from thick or heavy runtime to a nearly empty one. Go compiles everything into a single self-contained binary. This also has two stages, that means it is also a multi-stage build. Now let's compare it with the Node.js Dockerfile approach. What same multi-stage pattern, both are split into a builder and runtime stages. Builder stage installs dependencies. In Node it is npm install, in Go that is go mod download. Copy source code. Both bring in the app code after dependencies. Runtime stage is minimal. In Node has node18 slim, Go has scratch, literally empty, or alpine if we need certification, certain if we need shell or certs. CMD defines entry point. Node runs on node server.js, Go runs the compiled binary. So what's different between Node.js and Go language Dockerfiles? The concept. Language type Node.js is interpreted, whereas Go is compiled. Dependencies in Node.js npm install, that is node modules, whereas in Go it is go mod download for vendor modules. Build step in Node.js it is none. Runtime interprets JavaScript. Go language Go build produces a static binary. Runtime image in Node.js, no, it needs node runtime, that is node 18 slim. In Go language it can be scratch or no runtime at all because binary is self-contained. Output artifact in Node.js it is app plus node underscore modules. In Go language it is single binary main. CMD in Node.js, CMD is node server.js, whereas in Go it is /main. Now let's understand the summary of Go language Dockerfile. We can think of Go's Dockerfile as npm install plus build, that is copy binary to run the binary. That is first npm install plus build, then copying the binary, then running that binary. The big difference is Go doesn't need a runtime image like Node or Python. That is like an interpreter. Go is a compiler language. Once compiled, the binary is self-sufficient, so the final image can be scratch, literally empty, except for our binary. This makes Go images tiny and fast compared to Node or Python, which always needs their runtime present. If we know the Node, we know that stage 1 was builder, that feels like the same, installs dependencies, installing the dependencies, copying the code, preparing the artifacts. Stage 2, that was runtime, that is radically simple. Instead of carrying a runtime plus dependencies, we just ship one binary. That was about Go language Dockerfile and comparing it with Node.js Dockerfile. Now let's understand the Dockerfile of Java or Spring Boot. It's same, we are taking example of multi-stage Docker build for the Java or Spring Boot. Stage 1 is builder, stage 2 is runtime. We use JDK to build and a JRE lighter to run. Let's compare Java Spring Boot with Node.js Dockerfile approach. What's same? Multi-stage build, both split into builder and runtime stages. Builder stage installs dependencies. In Node it was npm install, in Java it is nv and clean package. This downloads dependencies plus jar. Copying the source code. Both bring in app code after dependencies. Runtime stage is Slim. In Node, it was Node 18 Slim. In Java, it is Eclipse Temurin 17 JRE Alpine. This is the Java runtime. CMD or entry point defines the entry point. Node runs on node server.js. Java runs on Java space -jar space app.jar. So what's different? Language type. In Node.js it was interpreted. In Java it is compiled to bytecode. Dependencies are npm install, that is node modules. In Java it is mvn package, that is downloading dependencies plus builds jar. Build step. In Node.js it is none. Runtime interprets JavaScript. In Java Spring Boot it is mvn clean package that produces a jar file, which is a compiled file that gets converted into the bytecode machine language. Runtime image. In Node.js it needs node runtime, that is node 18 Slim, for example. In Java Spring Boot it needs Java runtime JRE. Output artifact. In Node.js it is app plus node underscore modules. In Java or Spring Boot it is single jar, that is app.jar, which is a compiled app.jar. CMD entry point. In Node.js it is node server.js, which means if we run the application locally, we would be using node server.js as a command to run our application locally. So we add that CMD entry point in the Dockerfile. So in Java, it is Java -jar app.jar. Summary of Java or Spring Boot Dockerfile. Stage 1 builder feels familiar, installs dependencies, copying the code, preparing the artifact. The difference: instead of node underscore modules, Java produces a jar file that bundles compiled code plus dependencies. Stage 2 runtime is similar. Slim runtime image, copying the artifact, running it. Instead of node server.js, we run Java space -jar space app.jar. So the mental model would be node, that is installing dependencies plus running the JavaScript files. In Java it is compile plus package into jar plus running that jar with Java virtual machine. So that was about Java or Spring Boot Dockerfile, pairing it with Node.js Dockerfile. Now let's understand Rust Dockerfile. Let's compare it with Node.js 1. It's same. It has stage 1 planner or builder, stage 2 runtime, which means it is multi-stage Docker build. Now let's compare it with Node.js Dockerfile approach. What's same? Multi-stage build. Both are split into builder and runtime stages. Builder stage installs dependencies. Node, that is npm install. Rust, that is cargo chef cook plus cargo build. So in Node, npm install is the command that in the builder stage that installs dependencies. In Rust, the same command is cargo chef cook plus cargo build. Copy source code. Both bring in app code after dependencies. Runtime stage is Slim, which means Node has Node 18 Slim. Rust has Debian, Bookworm, Slim, or even Scratch for ultra minimal. CMD defines entry point. Node runs on node server.js. Rust runs the compiled binary. What's different? Language type. Node.js is interpreted language, whereas Rust is compiled language. Dependencies. In Node.js it is npm install, that is node modules. In Rust it is cargo chef cook that builds dependency layers. Build step. In Node.js none. The runtime interprets the JavaScript. In Rust it is cargo build space release that produces a binary. Runtime image. In Node.js it needs node runtime, that is node 18 Slim, for example. In Rust it can be Scratch or minimal Debian because binary is self-constrained in compiled languages. Output artifact. In Node.js it is app plus node underscore modules. In Rust it is single binary, that is my underscore app. CMD. In Node.js CMD is node server.js. In Rust it is app. Summary of Rust Dockerfile. Stage 1 builder. This feels familiar. This installs dependencies, copying the code, preparing the artifact. The difference: Rust uses cargo chef to produce optimized dependency caching like npm CI, but smarter for Docker builds. Stage 2 runtime. That is radically simple. Instead of carrying a runtime plus dependencies, we just ship one binary. This makes the Rust images tiny, fast, and portable, similar to Go. So the mental model would be Node that installs dependencies plus running the JavaScript files. In Rust, it is compiling the dependencies plus building the binary plus running binary directly. So that was about Rust Dockerfile and comparing it with Node.js Dockerfile. Now let's understand WASM or WebAssembly. This has same multi-stage build with 2 stages. Here we don't target a Linux distro, we target the WASM32 architecture. Comparing WASM with Node.js Dockerfile approach. What's same? Multi-stage build, both are split into builder and runtime stages. Builder stage installs dependencies. In Node it was npm install. In WASM, it is cargo build that compiles Rust code into .wasm. Copying the source code, both bring in-app code after dependencies. Runtime stage is minimal. In Node, it was Node 18 Slim. In WASM, it is scratch, literally empty, just the module. CMD or entry point that defines the entry point. Node runs node server.js. WASM runs the compiled .wasm modules. So what's different? Language type. Node.js is an interpreted language type. WASM is a compiled to WebAssembly language type. Dependencies. In Node.js, it is npm install, that is node_modules. WASM, that is run creates compiled into .wasm. Build step. In Node.js, it is none because runtime interprets the JS. In WASM, it is cargo build target WASM WASI that produces .wasm. Runtime image. Node.js needs Node runtime, that is Node 18 Slim. WASM doesn't need runtime at all. It is scratch. Module runs in WSL host. Output artifact. In Node.js, it is app plus node_modules. In WASM, it is single .wasm file. CMD or entry point. In Node.js, it is node server.js, which means when we run node server.js inside our folder in our command prompt, then that command leads to running the application locally. And that includes running the application with backend as well as frontend. So node server.js is the CMD, whereas in WASM, that same command is /app.wasm that is executed by the WSL runtime. Here WASL stands for WebAssembly Shader Language, which is a library and standard designed to translate WebAssembly modules into shader code that can be executed on a GPU. Now summary of WASM Dockerfile. Stage 1 builder. This installs dependencies, copying the code, preparing the artifact. The difference, instead of node modules that is in the node, Rust compiles everything into a WebAssembly module app.wasm. Stage 2 runtime. No Node, no Python, no JVM, just the .wasm file. Execution depends on WSL compatible runtime, that is WASM time, spin, or containered with WSM support. The container itself is just a carrier for the module, as this WSM concept is the GPU related, so it has different compatible runtime. For example, that would be WASM time, spin, or containered with WSM support. And also the container itself is just a carrier for the module. So the mental model would be Node, which installed dependencies plus runtime JS server. In WSM, it is compiling the Rust that produces .wasm. Then we run the module in the WSL host. That was about WASM Dockerfile and comparing it with Node.js Dockerfile approach. Now let's understand AIML serving Dockerfile. This is same multi-stage Docker build. Here we must use NVIDIA's base images, handle weights carefully. Now let's compare AIML serving with Node.js Dockerfile approach. What's same? Base image with runtime. Node has Node 18 Slim. AIML has NVIDIA/CUDA 12.1.0 base Ubuntu 22.04, which has Python plus GPU runtime. Dependency installation. In Node, it was npm install. Here in AIML, it is pip install -r requirements.txt, which means it is Python. Copying application code. Both copy project files into the containers. CMD defined entry point. Node has node server.js. AIML has Python 3 space -m space vllm.entrypoints.openai.api_server. What's different? Base image. In Node.js, it is lightweight node runtime. In AIML serving, base image is heavy CUDA-based GPU. That includes GPU drivers plus libraries. Dependencies in Node.js is npm install, that is node modules. In AIML serving, dependencies are pip install, that is Python packages with machine learning frameworks like PyTorch, VLLM. Artifacts in Node.js, it is application code plus node underscore modules. In AIML serving, it is model weights, that is /app/models plus Python packages. Runtime, Node.js runs on CPU only. AIML serving, it runs on GPU enabled, that is CUDA. CMD in Node.js, it runs on JavaScript server. AIML serving runs machine learning serving API, that is VLLM server. Data handling in Node.js, it is code plus small assets. In AIML serving, it is large model weights often mounted as volumes, not baked in. So in AI or ML, the concept of dependencies, runtime, data handling, CMD, all are having different approach compared to all we have discussed. Here, it doesn't depend on the CPU, which most of the other languages or their Docker files depended on. Whereas here, it depends on GPU drivers and its libraries, which is like the CUDA. It just doesn't run JavaScript server. It runs machine learning serving API as a CMD entry point, which is different. It doesn't just run node modules or app code, which was similar in every other Go or Java, etc. Whereas here it runs modeled weights, that is like /app/models plus Python packages. Data handling in other languages interpreted as well as compiled other than AIML was with code plus small or minimal assets, whereas in AI or ML serving, it is large model weights, which is often mounted as volumes, not baked in. Now let's understand the summary of AIML serving Dockerfile. Structurally, it is same. Base image, that is installing dependencies, copying the code plus running entry point. However, the big difference is GPU support and model weights. Instead of just code plus node modules, we are shipping Python machine learning frameworks plus massive model files. The base image isn't just a language runtime, it's CUDA, which provides GPU acceleration. CMD doesn't start a JavaScript server, it starts an machine learning inference server here, that is VLLM mimicking OpenAI's API. So the mental model or our approach would be Node was installing dependencies plus running JavaScript server. Here in AIML, it is installing machine learning dependencies plus loading the model weights plus running the inference server. So that is it for the video today. We have discussed Dockerfile with known technical stacks and compared that with Node.js Dockerfile.